Hello everyone and welcome to FAIRDM's 2017 webinar series. Thanks for joining us for the fifth webinar of the season. I'm Natalie Stanford from the FAIRDM community and I will once again be hosting the webinars this series. For those of you who don't know, FAIRDM is an initiative to support researchers, students, trainers, funders and publishers. In fact, anybody interested in data management, in better data management practices. We offer software, advice, expertise and training which make managing your data and models in life sciences easier. You can find more about FAIRDM at our website, which is at www.fairdm.org, or you can look at us on Twitter at FAIRDM_EU. And if you have any questions regarding FAIRDM, you can get in touch with me at community@fair-dom.org. We've got Bjoern Gruening speaking today, and he's going to be talking about Conda and Containers for a sustainable bioinformatics infrastructure. Bjoern Gruening is with the bioinformatics group at Albert-Ludwigs-Universität in Freiburg in Germany, and he heads the Freiburg Galaxy project and is an active driving force in the Galaxy community. He primarily contributes to the project by developing components for reproducible and accessible research, and he's also been heavily involved in organising prominent community meetings, including Bioconda Contribution Fest, Swiss-German Galaxy Data, and Galaxy Development Ops Workshop, and much more. In addition to this, he has research interests in data visualization, computational chemistry, and epigenetics. So I'm just going to hand over to Bjoern now.
Thanks, Natalie, for the kind introduction. Yeah, so thanks everyone for joining. Let's start right away. Today, I would like to talk about a FAIR tool infrastructure. So I want to talk about the FAIR principle from a bottom layer of our bioinformatic infrastructure. So more about how do we exchange tools, how do we install tools, and how do we make it findable, accessible, interoperable, and reusable. So, for example, you can think of the challenge of finding, creating, and exchanging tool dependencies of a specific tool you want to run or a workflow you want to run. The question is, how do you use these tool dependencies in your specific environment, let's say in your HPC or cloud environment? And how do we make tool dependencies work across different platforms, across different operating systems, across different cloud providers, and so on? But also, how do we store actually these units of tools, of dependencies? How do we archive it? Do we archive actually at all our tools? And how do we annotate them to make them, again, findable and accessible for our users? So I hope I will cover all aspects during my talk. So let's start to have an eagle-eye view on how tool deployment or sustainability in science usually work. So usually you have a question you want to answer, you take tools or you develop a chunk of code, and then you deploy it to some compute infrastructure, and then you analyze your data. So that's, I would say, is a normal eagle-eye view on normal data processing. But usually there's a step in between from development of code, actually, how do you deploy that code? There's a packaging step in between. And since decades, people have developed package managers, and package managers, from their definition, which I have outlined here, is charged with the task of finding, installing, maintaining, and uninstalling software packaging upon a user's request or comment. And this is what I would like to discuss a little bit at the beginning. So let's look at package managers, which we all know, like very distribution-specific package managers like Yum or DPKG from Debian. Then there are language-specific package managers like CPAN, CRAN, Bioconductor, or pip. And there are more recent ones, which I would also label as kind of package managers, where you think of Docker and containers, which also kind of package tools and give them as a reusable unit to a user or to different infrastructures. The problem is there's no really standard available. Debian based distributions or Fedora based distributions have a complete different package manager. They don't share their resources at all. CPAN and CRAN have more or less their own package manager and share very little. And this is kind of disappointing as far as I see it. Especially for bioinformatics, because in bioinformatics we have a huge turnaround in tools. So because techniques and data are changing so dramatically and so fast, all our tools are also changing pretty rapidly. An RNA-seq pipeline I used on a regular basis 2-3 years ago is completely replaced by new tools nowadays. And the question is, how can we keep up with these fast process of tool development? How can we create a package manager that actually works on different operating systems? Debian, Fedora, cloud environment, HPC environment. How can I have a package manager that is programming language agnostic? I mean, everyone has its favorite programming language, and I would like to have a package manager that is capable of doing most of them or even all. Also, a very crucial point is we need to, at least in bioinformatics, I think we need to install packages in our home directory. So we usually don't have root privileges on HPC environments. And because we need to have high performance computing in our daily analysis, we need to be able to install tools in these environments as well without asking an administrator to install certain tools. But for reproducible reasons, and I think bioinformatics is here a front runner in this field, if you look at other communities, we also need to have multiple versions of the same tool installed for reproducible reasons, to run a workflow with to run different workflows on the same input data set. And last but not least, because of the huge turnaround, I think this package manager should be easy to maintain. A few years back, actually a company called Continuum developed a Conda package manager, which I think fulfills all these requirements. And this is what I would like to introduce you today. Conda as a unified package manager for bioinformatics or for scientific computing in general that bridges the gap between a variety of programming language and a variety of deployment environments, and how all this relates together to containers, I will talk later. So what is Conda? So Conda is an open source package manager. It is independent of any programming language. It's fast, robust, and it's easy to actually manage your packages. So Conda install deep tools will install your the deep tools package with all these dependencies, and it's able to install and manage multiple versions, for example, of deep tools, or manage multiple versions of R. So you can have R 2.3 and R 3.3 next to each other with different packages and so on. How do you define such a package? And this is where this easy maintenance comes into play, is such a file. So this is a file of deep tools. So this is actually the package which we need to write to create a Conda package. And this is called a meta.yaml file. And as the name suggests, it's a YAML formatted text file. And you see at the top is just the name of the package and the version. You define the source of the package. So this is usually the tarball, and a checksum, so that actually during download it's checked that it's a correct content. And then there's kind of an interesting thing here. So you have build dependencies, which just specifies, hey, I need to have a GCC compiler and a Python environment and setup tools and a bunch of other Python libraries. But then I have also runtime dependencies, which includes Python, but no GCC, because I don't need GCC in my runtime environment. And I also don't need setup tools actually in my runtime environment. And then there's a test section where I actually can test this package. So this package will be built, it will be pre-compiled, and then the pre-compiled binaries or the pre-compiled scripts gets tested automatically by Conda during package creation. And then there's, and the last but not least, there's a list of metadata which we can extend, and where actually plans exist to extend that extensively with more metadata, for example, to enrich bio.tools, so a tools registry to make it then easy to search for tools. But this is, yeah, in the future. I would like to mention that the package, the tarball actually, which we specify in this file, we need to rely that this tarball exists, right? So if we include here a URL that is not persistent, we cannot rebuild this package. I mean, it's not strictly needed to rebuild this package because we ship here pre-compiled binaries, but still, for the reproducibility reason, it would be nice if we also capture this tarball. And yeah, I will talk later about that, how we do that. The second file which you need to create such a package is called a build.sh script, which really only contains the setup.py install command in this case. If you have a C, C++ library or a tool which you really need to compile, this build.sh script can be simply configure make install, for example. So essentially what Conda is doing here, and I think it's easy as it can get, you still have the build commands, which you cannot avoid. I mean, you need to compile or you need to install your stuff, but this is separate in a bash script. And then you have a lot of metadata that actually defines your dependencies, the hierarchy of your dependencies, and it contains tests in just 2 files. And given these 2 files, I can build this package with a single command called conda build, and then the directory where these 2 files are located. And that's it. After compilation or after building, you get a tarball which contains your package and you are done. And now you can upload it to a registry and then people can simply install with Conda, install DeepTools your package. And that's it. It's easy as it can get, I think. The thing is, now we try to build a community about this package manager. And especially for the bioinformatics community, there is a project called BioConda, which is now 1.5 years old, which tries to unify this build process. So for example, to make it really an independent package, you probably want to compile this package into in a unified build environment with hopefully no other libraries included. So for example, just imagine you have zlib or something like that already installed in your environment where you compile this package. These libraries can sneak into your build environment. And because we don't want to do that, we can just run this conda build command in a Docker container, which more or less don't contain any pre-installed libraries or packages. And this is where all these community aspects come together and where BioConda really shines. So BioConda is a huge community around this package managers, maintaining a lot of bioinformatics packages, but also maintaining a build infrastructure. So maintaining Docker images in which you execute this build command, but also maintaining documentation and package upgrades and so on. And we keep a very nice contact to other Conda communities, for example, the Conda Forge community, where Conda Forge is more responsible for the general purpose packages, like CMake or AutoTools package or the xlib libraries or the Boost library, for example. And BioConda really can concentrate on bioinformatics packages. But because we are depending on Conda Forge, we have a kind of nice relationship between them, and we try to synchronize our build infrastructure with them and have regular meetings with them. In this slide, you can see, just as a brief introduction, the BioConda website, where we collect informations about how you install Conda, how you install our packages, how you upgrade packages, all of that. But we also maintain a huge section about contributing actually a recipe to make it as easy as possible for you to contribute your tool into the Conda package managers. And as you see at the bottom of this slide, there are special sections for R packages, Java packages, Perl packages. So all of these programming languages have their unique features, let's call them features. And we have collected our experience here to make it really easy to contribute to this project. Currently, Biocon has already 2,450 packages. You can contribute over GitHub. It's a really community-driven project, so we have more than 170 contributors that maintains packages, that contributes new packages, that try to answer questions. We have special core groups, so special expertise in Perl, for example, or people that care a lot about OS X packages, and they can help with debugging OS X packages, or experts in the R programming language, so that you can actually ping and get help from these core groups. But this project is more or less all about community. And as you see, in the last 1.5 years, we have more than 3,000 merge pull requests from all over the world. And what we actually see is that upstream maintainers of tools contributing their packages to Biocon, which is actually neat. Because if you have upstream maintainers maintaining their own packages, they are the experts. They know the best compilation flags. They know the dependencies when they changed and so on. So this is actually where we want to go, right? That the upstream package maintainer is providing a nice package for us, which can be used in all kinds of different environments and are fair in the fair in principles. But since a few years, the new cool kit is called containers, right? So everyone is trying to create containers or at least provide a container, ship a container. There are many workflow engines that are built on containers and so on. And these traditional package managers, where I consider Conda as well, are still cool, but I think the more traction getting these new feature of Linux containers. But again, there's no real standards, and my philosophy was more like embrace new technology, but make them interconvertible. So what we did is we created a system that takes a Conda package and converts the already pre-compiled binaries into Docker, Rocket, or Singularity containers. So essentially what's happening is you have this packaging, you have your Conda package, and now we will generate you all different container technologies which you want to use or which you can use automatically out of it. So I'm not a fan of writing these Docker files and really compiling or putting in configure, make, install again in the Docker file. I don't think this is very transparent. I don't think that you can trust many Docker images on Docker Hub. So the intention here is that we create a system that automatically converts Conda packages that are community maintained, that are already tested, and convert all these different entities out of it, test these entities as well, and then push it to Docker Hub, to Rocket, or to an FTP server and share it with the community. Another aspect of this approach is that if you're really concerned about reproducibility, this is a very nice way to achieve reproducibility across different technologies. Because please remember that these are pre-compiled binaries, and these pre-compiled binaries are the same in Conda, in Docker, in Singularity, and in Rocket. So if you use other technologies, so if you use your package manager on your Fedora system and you install SemTools, and then you take a Docker container with SemTools or a Singularity container with SemTools, you cannot rely that actually this is the same SAMtools version. If you look it up and if you pin the versions and you can rely that it's the same version, you cannot be sure that actually all these technologies have used the same compilation flags or actually include the same dependencies and so on. And with this system, which I am introducing here, we can really rely that the same binary is ending up in all different technologies, and hopefully whatever technology comes next and will replace containers, we hopefully can just go back, take Conda packages and just interconvert them and embrace these new technologies and deliver our great tools in bioinformatics to our favorite environment. How this works in the Docker way is we have created a layer donning approach to build containers that doesn't involve Docker files at all. It's completely automatized and it's all happening on Travis, so on a continuous integration setup. The point is here that we really just take the binaries from one technology and putting it in the other technology. So there is no Docker file needed. Once you trust this build chain, which are all publicly available and which are happening publicly on public continuous integration instance and on GitHub, as soon as you trace and trust these build process, you can trust the artifacts we build automatically for you for different technologies. And this is where biocontainers comes into play. So biocontainers is a community dedicated for containers and maintaining documentation about containers, how to develop training material for containers, developing documentation on how to run containers in different environments, and to define standards and best practices for container deployment, but also for container creation. So what we do here is, as soon as you create a pull request with a bioconda package, we will create you a Docker container, a Rocket container, and a Singularity container automatically, and push that into a biocontainers namespace. So all this becomes magically available as biocontainers project on Docker Hub, on Quay.io for Rocket, or on some FTP server or a Singularity hub for Singularity. There are plans to include actually or to generate module files automatically as well, but this is for the future, and if anyone wants to contribute, let me know. But yeah, let's pinpoint the main idea here. You contribute 2 text files to bioconda. This is the meta.yaml file and the build.sh file. And then we will generate you all these nice fancy technologies out of it. Automatically, very transparent, and the same binary will end up in all these technologies. Yeah, and this is, as a roundup, I would like to talk now about findability from the other perspective. So if you want to find a container for a specific package, you need to have a unified namespace across these technologies. So just assume you are searching for SAMtools, and you want now to have a Singularity image for SAMtools or a Docker container for SAMtools. You want to have a unified namespace. And this is where we just developed a command line tool, so you can just do mult search.s SAMtools, and you will get links for all SAMtools version, which we have for containers, which we have for Conda, and so on. But all of this will also be offered as on a website. Actually, biocontainers has a registry where all this gets munched together, and where you can also search on a web interface. Who is using that already? So there are many projects like Cyverse and Open Science Grid that using the bio containers. SnakeMake is using the bioconda containers, and actually Johannes Köster, the SnakeMake developers, is one of the driving forces behind bioconda. And the Galaxy project can use all of these technologies. So you as administrator more or less decide how you want to resolve the dependencies of your specific tool or a specific Galaxy workflow. And Galaxy will then automatically pull down the needed images or packages, which is only possible because we have this unified namespace, and the container or the Conda package has more or less the same name. And I can predict the name automatically if you just tell me what you want to do or what you need. So I hope I could convince you that we have a findable, accessible, interoperable, and reusable infrastructure here. And with that, I would like to thank very much the entire communities. And this is a large community. So especially thanks to BioConda community. So Johannes Köster, Ryan Dale, and all the other 170 contributors. Thanks a lot for this amazing project and for collecting so many high quality recipes in such a short time. Thanks a lot to the biocontainers project. So just the two representatives here, Yasset and Philippe, they really did an amazing job in helping to setting up these biocontainers infrastructure. But also thanks a lot for Travis. So continuous integration changed a lot in the last years, how we deal with testing and integrating of different projects. And Travis is just one of these continuous integration systems. But thanks a lot that we as scientific community can use that for free. The same goes for Docker and for all these registries which we can use for free. Conda and Anaconda also provides us with space where we can store our packages actually. And last but not least, thanks to Elixir and the German network of bioinformatics infrastructure for supporting this project and these ideas to have finally a fair and sustainable tool infrastructure. Thanks a lot. For questions, please get in contact. Thanks.
Thanks very much, Bjorn. So yeah, as this is a pre-recorded webinar, if you have any questions, it's best to get directly in contact with Bjorn. Bjorn, do you have a preferred contact?
Via mail, I guess. I'm also on Gitter. So the biocontainers and BioConda has a Gitter channel. You can also ask questions there, or on GitHub, of course. Just create an issue if you have questions, and I will try to answer. Otherwise, just per personal email.
Okay, that sounds good. And if you can't find Bjorn's contact details, you can always contact community@fair-dom.org, and I'll pass on any of your questions directly to Bjorn anyway. So once again, thanks very much, Bjorn, and thank you for the lovely presentation. And I hope you get lots of questions later on.
Thanks for organizing, and thanks for listening all.
Okay, thank you very much. Okay, bye-bye.